In the last lecture, we were discussing the application of correlations in one-dimensional balance equations for mass or energy in situations where, for example, the temperature or concentration of an object is varying as a function of time. Okay, if you have a sphere that is cooling in a liquid, for example, in a fluid, for example, due to the temperature difference, the temperature of the sphere decreases as time increases because of the heat transfer from the sphere to the fluid, assuming that the fluid is at a constant temperature. In such a situation, is it possible to use a correlation for the average flux from the surface of the sphere? The assumption that was made in deriving the correlation, for example, the correlation shown here, the Nusselt number is equal to 2, okay, in the limit of low Peclet number. The assumption that is made here is that the object is at steady state. You have an object at a constant temperature in a fluid at a different constant temperature, and the flux is calculated. Okay, that is the assumption made when the correlation is derived. In this particular case, the temperature of the object is changing with time. The correlation can still be used if the time required for the change in temperature of the object is much longer than the time required for the system to reach steady state once an object at a fixed temperature difference is introduced. Okay. If you have a configuration where the entire system is at the same temperature, the object plus the fluid are at the same temperature at time t is equal to 0, and at time 0 you increase the temperature of the object to some finite value. Okay. It will take some time for the temperature of the fluid around the object to reach its steady state value. That steady state value is of course a higher temperature closer to the object and a lower temperature further away. We will solve for that later. So, the time it takes for the fluid temperature field, the temperature variation in the fluid, spatial variation of the temperature field to reach its steady state value. Okay. If the time required for the surface temperature to evolve on the surface of the object is much longer than the time required for the temperature field around the object to reach its steady state value, then you can still use a correlation that is derived at steady state. And I told you that the time required in the limit of low Peclet number, where the transport is dominated by diffusion, the time required for the temperature field around the object to reach its steady state value is this diffusion time. Okay. The characteristic distance squared divided by the diffusivity, thermal diffusivity for heat transfer and mass diffusivity for mass transfer. So, that is the diffusion time, provided the time taken for the temperature of the object to evolve due to the heat transfer out from the object is much longer than the diffusion time. You can assume that at each instant the system is at steady state, and therefore use a correlation for the Nusselt number that is derived at steady state. Another situation was shown on the right here, where you have an object which is elongated and the temperature changes as a function of position on this object. And since there is a temperature variation, you cannot assume that you have an object at constant temperature in a fluid at another constant temperature, because the temperature of the object is varying. The steady state, correlation derived at steady state can be used only if the length scale for the variation of the temperature around the object is much smaller than the length scale for the characteristic dimension of the object itself. The length scale for temperature variation around the object is much smaller than the length scale for the characteristic length of the object itself. So, that locally you can use a steady state approximation and use a correlation that is derived for an object at a constant temperature in a fluid at a different constant temperature. Okay. For diffusion dominated transport, the characteristic length scale for diffusion is the same as the characteristic dimension of the object, and therefore, for diffusion dominated transport we cannot use a correlation that is derived for a constant temperature object in a fluid of another constant temperature. That is, for a situation where the temperature difference is a constant, that correlation cannot be used in general, because the length scale for diffusion is comparable to the dimension of the object. And we had looked at examples in diffusion dominated transport where the characteristic time for the evolution of the temperature of the object is much greater than the diffusion time, okay. Or alternatively, in cases of a dissolution of a particle where the characteristic time for dissolution is much larger than the time required for the concentration field around the object, in this case to reach a steady state value. Okay, so, those we examined. The next is to look at natural convection. Natural convection at high Peclet number, okay, the limit of high Peclet number, where convective effects are large compared to diffusive effects. Okay. You have a rapid flow past the object. Okay. Even though convective effects are large, diffusion cannot in general be neglected, okay, because convection only transports mass energy along the fluid streamlines. At the surface of the object itself, whether it is a solid object or a gas bubble, there is no penetration condition at the surface. Okay. The velocity perpendicular to the surface is 0, and therefore, transport perpendicular to the surface has to necessarily take place due to diffusion. So, for example, if you had an object of a higher temperature in a fluid of a lower temperature, for example, the energy from the object will be transported due to diffusion perpendicular to the surface, and it will be swept downstream due to the fluid flow past the object. In the limit of large Peclet number, the energy that is being conducted from the object will be swept rapidly downstream, and therefore, the temperature difference due to this energy transport from the surface will be restricted to a thin region near the object. Okay. The thickness of that region depends upon the flow conditions at the surface and the Peclet number. Okay. It depends upon the flow conditions at the surface and the Peclet number. The flow conditions again depend upon the Reynolds number, ratio of inertial and viscous stresses, as well as the boundary condition at the surface, whether there is a no slip condition at the surface or whether there is a non-zero velocity at the surface. Okay. So, in these cases the length scale for diffusion is actually much smaller than the dimension of the object. Okay. If LD is the length scale for diffusion, then the time scale for diffusion, you just get it out of dimensional analysis as LD square by the diffusivity. Okay. So, that is the characteristic time for diffusion for the temperature field to develop in this thin boundary layer, or the concentration field to develop in this thin boundary layer when the surface concentration or temperature is changed. So long as the diffusion time is much smaller than the evolution time for the temperature field in the object, you can use a steady state approximation correlation for natural convection that is derived based upon the steady state approximation. So, let us briefly summarize the characteristic length and time scales for different configurations. Okay. Last time I had told you that there is a distinction between objects which are have a no slip condition at the surface, where the surface is solid, and objects which have a slip condition at the surface, where you have a non-zero tangential velocity at the surface. So, let us examine that. Okay. First, we will examine the flow around a particle. Okay. Okay. So, if you had a solid particle for example, okay, you would have a no slip condition. So, if you have Vfs is the free stream velocity, and you have flow around a particle for large Beckley number, okay, where convection is dominant, and small Reynolds number where the flow is laminar. Okay. For small Reynolds number where the flow is laminar and large Beckley number when the convection is dominant. Recall I had told you that you can simultaneously have the limit of large Beckley number and small Reynolds number, because momentum diffusion is much faster than mass diffusion in liquids. Okay. In gases they are comparable and therefore, this regime does not exist, but in liquids the mass diffusion is a very slow process because it involves the physical transport of molecules, and therefore, whereas momentum diffusion does not involve physical transport, it could be due to intermolecular forces, and therefore, you can simultaneously have high Beckley number and low Reynolds number. Okay. In this case, if I have an object of characteristic dimension d, okay, in the limit of high Beckley number, and there is a no slip boundary condition at the surface, the velocity has to decrease to 0 at the surface, then if the temperature disturbance due to the higher temperature of the object, okay, if you had an object with temperature T naught at the surface and T infinity far away, the temperature disturbance due to this higher temperature of the object will be restricted to a thin what is called a boundary layer close to the surface. The thickness of this boundary layer is scales as the Beckley number power minus 1 by 3. Okay. In the limit as the Beckley number becomes large, okay, in the limit E is large compared to 1, the thickness of this boundary layer scales as Beckley number power minus 1/3. Okay. And in fact, because the thickness of this layer scales as P power minus 1/3, the correlation for the Nusselt number is the thermal conductivity times the temperature difference divided by a characteristic length. In this case, that characteristic length is this diffusion length, which is P power minus 1/3, and therefore, you get Nusselt number going proportional to Beckley number power plus 1/3. Okay. So, basically the Nusselt number will scale as the inverse of this characteristic length. Okay. This characteristic length is P power minus 1/3 times the diameter. Okay. The ratio of the characteristic length for diffusion, okay, LD by the diameter, characteristic dimension of the object is P power minus 1 by 3. Okay. And because the flux, the temperature difference is divided by this characteristic length, the Nusselt number will scale as P power plus 1/3. Okay. So, that is the characteristic dimension for the flow past an object in the limit of Beckley number large compared to 1 and Reynolds number small compared to 1. Okay. On the other hand, if I had, for example, a gas bubble, okay, which is subjected to a similar free stream velocity, okay, of diameter d, okay, at the surface of which I have the tangential velocity is non-zero. Okay, the tangential velocity at the surface is non-zero. So, the interface is mobile in this case. Okay. In this case as well, you get a boundary layer, okay, around the object, okay, because whatever mass or energy that comes out of the object due to diffusion perpendicular to the surface gets swept downstream rapidly, and in this case the ratio of the diffusion length by the diameter is equal to P power minus half, okay, Beckley number power minus half in the limit of high Beckley number. Okay. So, this is for the flow around an object in the limit Beckley number large compared to 1 and Reynolds number small compared to 1. Okay. Now, what about in the limit Okay. What if I have a laminar flow in the limit of high Peclet number and high Reynolds number? Okay. In that case, as you know, the velocity, the Nusselt number does not depend on the Peclet number alone, because the flow does not transform in a self similar manner. The flow pattern does not remain the same as the velocity increases at high Reynolds number. Okay. Okay. In that case also, for the flow around an object, you have a boundary layer. Okay. For the flow around an object with a no slip condition at the surface, you have a boundary layer, whether it is for concentration or for momentum. Okay. And the thickness of this is classically given by the LD by D is equal to RE power minus 1 by 6 PE power minus 1 by third. Okay. Alternatively, if I write Peclet number as RE times PR, this will become RE power minus half times PE per PR power minus 1 third. Okay. Note that the Peclet number is just the product of the Reynolds number and the Prandtl number. Okay. This is for no slip boundary condition at the surface. For a slip boundary condition at the surface, it turns out that this relation still holds. Okay. Even in the limit of high Reynolds number. Recall that I told you that for the high Reynolds number flow around a solid particle, you have a sequence of flow patterns starting with an asymmetry about the mid plane perpendicular to the flow, followed by a separation bubble at the rear, followed by the vortex shedding, and then turbulence in the upstream boundary layer. Okay. This is valid for the laminar flow. Okay. This is valid only for laminar flow in the boundary layer, okay, at high Reynolds number. That sequence is not present for the flow around a bubble. I had told you that, provided the surface of the bubble is sufficiently clean that there are no surfactants or anything. What you have for a bubble is potential flow at high Reynolds number, and in potential flow, basically the same kind of relationship applies for the flow around a bubble as well. Okay. So, those are the sequence of patterns for flow around a particle. Okay. Now, for the other case we can consider is flow around a flow past flat plate. Okay. And as you recall, in the case of the flow past a flat plate, you had a free stream velocity, and then you had this momentum boundary layer, which was initially laminar and then it became turbulent. Okay. In the laminar region, okay, the boundary layer thickness went as x power half, whereas in the turbulent region it went as x power 0.2. Okay. Okay, if you recall, we had done this, okay, where x is the downstream distance from the edge of the flat plate. Okay. In this case as well, if you have a flow past the surface, the boundary layer for momentum or energy, okay, so I am sorry, the boundary layer for mass or energy, okay, the boundary layer thickness for mass or energy for a laminar flow okay, this diffusion length by the diameter is equal to RE power minus 1 by 6 PE power minus 1 by 3. Okay. It is the same as what you have for the flow around an object, okay, for the laminar flow. Okay. It is different, of course, for a turbulent flow, and that is a much more complicated picture, which I will not go into in detail in this lecture. Okay. And finally, we can examine internal flows. Okay. We can examine internal flows. Okay. So, for example, the flow in a pipe. of diameter d and length L, okay, a pipe of diameter d and length L. Okay. So, in this case, okay, in the limit of high Peclet number, okay, in the limit of high Peclet number, laminar flow. In the limit of high Peclet number, any energy that is being conducted from the wall of the pipe is rapidly swept downstream, okay, due to convection. Therefore, the disturbance to the temperature is restricted to a thin region close to the wall whose thickness is much smaller than the pipe diameter, okay, because any energy that is conducted from the wall is rapidly swept downstream by the strong flow. Okay. And this characteristic boundary layer thickness for a pipe flow, okay, for a laminar flow, is scales as LD by the diameter is equal to P power minus 1 by 3, okay, and D by L power minus 1 by 3. Okay. So, it has a high Peclet number limit, P power minus 1/3 times D by L power minus 1/3 is its thickness, and this also we will derive later. This is valid only for the Peclet number much smaller than L by D. Okay. Note that we have considered the high Peclet number regime. Okay. Note that we have considered the high Peclet number regime, okay, and therefore, the diffusion length divided by the diameter is going to be small compared to 1, because P power minus 1/3 times D by L power minus 1/3. Okay. So, this product will be small compared to 1. Okay. So, I am sorry, I have said it the other way around. For L by D, much smaller than Peclet number. Okay. Yeah, and RE much greater than 1 and PE much greater than 1 for the flow in a pipe. Okay. Once L by D becomes comparable to the Peclet number, then what happens is that this boundary layer thickness becomes comparable to the pipe diameter, and then the diffusion length then becomes comparable to the pipe diameter. Okay. So, this is the diffusion length for a pipe flow, okay, and once again we will derive that later. The other case I will consider is flow of a vertical film. Okay. If you recall, we had earlier done the flow of a film down an inclined plane, and the velocity profile looks something like this. We had calculated the velocity profile, okay, in this case for an inclined plane flow. This vertical flow is the same as that inclined plane flow, except the angle is 90 degrees. In this case as well, if this is the start of the contacting section, let us say that you had a gas species that was diffusing into the film and then getting convected downwards. Okay. And if the Peclet number, okay, based upon the film thickness, okay, film thickness h, which will be h times the average velocity by the diffusion coefficient, okay, that is the Peclet number. If this is large, okay, then the penetration of this solute into the liquid film, it penetrates to an extent which is small compared to the thickness of the film. Okay. It penetrates to an extent that is small compared to the thickness of the film, and this is the characteristic length for diffusion. Okay. And that characteristic length for diffusion in this case divided by the thickness goes as the Peclet number per minus half into D by L, sorry, H by L. Per minus half, okay, where L is the total length of the film. Okay. This is an example where the condition at the interface is a non-zero velocity, just like we had in the case of a bubble. Okay. Flow in a pipe is an internal flow with a zero velocity at the wall, as in the case of the external flow around a solid particle. The flow down in a thin film is an external flow in which you have a zero shear stress condition at the surface, a finite velocity at the surface, just like we had in the bubble. And in that case you can see that these exponents turn out to be half. Okay, these exponents in those cases turn out to be a half. And we have another condition here, which is that L by H much smaller than P. Okay. In this case the diffusion length is going to be much smaller than the thickness of the film. Okay. So, in those cases we can assume a steady state approximation, okay, for the correlations and use those correlations in order to determine what is the rate of change of the temperature of a solid object, for example, in a fluid flow. So, let us take an example. Okay. I have a steel sphere with diameter is equal to 1 centimeters. Okay. The temperature, initial temperature, okay, initial temperature is equal to 300 degrees centigrade. Okay. And I have fluid, okay, air flowing past the sphere with the free stream velocity, okay, of the air is equal to one meter per second. Okay. And the question I am asking is, how long does it take for the velocity of the sphere to decrease to 100 degrees centigrade. Okay. The air has temperature Vfs is equal to 1 meter per second, and the temperature of the air is equal to 0 degrees centigrade. Okay. So, this air is cooling the sphere, okay, and what we would like to find out is how long does it take for the temperature of the sphere to decrease from 300 degrees centigrade to 100 degrees centigrade. Okay. So, for that we need the properties of air. Okay. So, I will give you the properties of air. Rho air is equal to 1.25 kg per meter cubed. Okay. K of air is equal to 2.4 into 10 power minus 2 watts per meter per degree centigrade. Okay. Cp air is equal to 10 power 3, okay, joules per kg per degree centigrade. Okay. And the density and specific heat of steel, rho s is equal to 8 into 10 power 3, 8000 kilogram per meter cubed, and the specific heat of steel is 500, okay, joules per kg per degree centigrade. Okay. So, given these properties, I need to find out how long it will take for the temperature of the sphere to cool from 300 degrees centigrade to 100 degrees centigrade when air is blown past it at a velocity of 1 meter per second. Okay. So, that is a problem. I will start in the next lecture with solving this problem before we go on to solve the problem of a dissolution of an object due to mass transport in natural convection. These two problems we will consider in the next lecture. I will see you then.